Okay, AP Statistics students. So yesterday in class, we collected some data on M&Ms and their color distribution. You'll be needing that data, or I'll be using that data to teach this lesson. You guys all entered your data into that spreadsheet, and so I've kind of collected that and we'll show you the results. In Chapter 11, Section 1, we're going to learn how to carry out a chi-square test for goodness of fit. Now, I know that that's bad language, bad English skills, but that is the name of the test, is goodness of fit. So, chi-square test for goodness of fit. When do we use it? Are we going to be able to recognize when that's the significance test that I should carry out? It's usually pretty easy to do so. By the way, this is the Greek letter chi, and so we'll be naming this the chi-square GOF test, just so we don't have to write goodness of fit all the time. So in Chapter 9, we learned how to carry out the one proportion z-test. Well, I want to compare a one proportion z-test to a chi-square goodness of fit test. In the data that we collected from the M&Ms, I found out that 310 of the 1,300 M&Ms were blue. Well, the Mars company says that on average, when you open up a package or a container of M&Ms, I use one of those great big containers from Sam's Club, that 25% of the M&Ms in that container should be blue. That's their claim. So I could have said, carry out a one proportion z-test to see if the percentage of blue is what they claim it is. And so if you look on the left side as a Chapter 9 review, I said the null hypothesis is P blue equals 0.25 and the alternative is P blue is not 0.25. I calculated P hat for blue. 310 divided by 1300 is 0.238. So 23.8% of the M&Ms in that big old container I used yesterday was blue. The standard deviation of P hat blue turned out to be 0.25 times 0.75 divided by 1300. Square root of that, 0.012. So I took 0.238 P hat minus 0.25 divided by 0.012 to get a z-score of exactly -1. That's pretty unusual. I used my calculator to run a one proportion z-test, and it told me that the p-value was 0.32. That is, this was 0.16 and this was 0.16. So since that p-value was so large, I said, don't reject the null. Well, if I don't reject the null, that means there's evidence that the percentage of blue really is 25%, or as we're supposed to say, there's no evidence that the percentage of blue is not 25%. In other words, it seems as though the percentage of blue is good to go. It seems like it is roughly 25%. Well, what if instead of checking one color, what if the statistician working at the M&M's factory wants to check all of the colors at once? Well, he's already carried out a one proportion z-test and found out that the percentage of blue is good. Well, he says, well, now, why don't I just run 5 more one proportion z-tests? That would be horrible, except technology, it wouldn't be too bad. So what I'm trying to tell you is, instead of running a bunch of one proportion z-tests, there's a way that you can check multiple proportions against multiple claims all at the same time. And that's a chi-squared test for goodness of fit. So when you're carrying out a chi-squared test for goodness of fit, just like any other significance test, the first thing you do is state your hypotheses. Now, what's unusual about the chi-square test is that the hypotheses, we usually use words. You don't have to, but usually people do. When you state the null hypothesis for a chi-square goodness of fit test, your null hypothesis should be a claim about the distribution of a single categorical variable. So listen to this null. The distribution of the colors in the container of M&Ms, I bought a big old container instead of bags, is the same as the claimed distribution. Do you remember how most null hypotheses is something equals something? Well, think of the null hypothesis for a chi-square goodness of fit test as sort of being the same thing with words. The distribution across this categorical variable is the same as what was claimed, equal to. And then the nice thing about stating that null hypothesis is the alternative hypothesis use the exact same words as the null, but say is not the same. Say it exactly the same way, but put that word not in there. Now, there are alternative ways to write the hypotheses. I could have said that the null hypothesis is the percentage of brown is, they claim, 12.5%. The percentage of red is claimed to be 12.5%. The percentage of yellow and green are also claimed to be 12.5%. Percentage of orange is 25% and blue is 25%. So you could list each individual percentage that was claimed about your population. I don't think so. You'll never catch me doing that. However, sometimes I do use this alternative in the place of this alternative. At least two of the proportions listed above are incorrect. You can say at least two of the proportions are incorrect. Now, why do you have to say at least two? Well, if one of the proportions is wrong, then there must at least be one other one that's wrong that's making the other one tip and be wrong. Okay, so you state your hypotheses. Now, instead of doing the plan, I'm going to show you the do part and then show you the plan part because I just want to get through some things. So, to carry out a chi-square test for goodness of fit, the first thing you want to do is make a table. Now, a lot of times a partial table is already provided for you, a table that contains the observed counts. So imagine that what I did was I made a spreadsheet of the counts of M&Ms that all of you made by entering into the Google form. So I found out that 138 total M&Ms were brown, the collective. 170 yellows, 170 reds, 157 greens, 355 orange, 310 blue, for a total of 1,300 M&Ms. A lot of M&Ms. Okay, so the first thing you do is make sure that you have a table of observed counts. Okay, the next thing you're going to do is you're going to make a new column where you put in the expected counts. Well, do you remember that the brown claim, don't write this, when you're doing a problem formally, was 12.5% of M&Ms are brown. So how many browns would I have expected? 0.125 times 1,300. So if I grab my calculator, 0.125 times 1,300 is 162.5. So I would have expected about 162, 163 brown M&Ms. Well, isn't the claim for yellow, red, and green also 12.5%? So I guess these happen to be 162.5s as well. Okay, now, blue and orange, the M&M's company says 25% of M&M's in a container should be orange. So 0.25 times 1,300 would tell me how many oranges and blues I would have expected. So let's see, 0.25 times 1,300 is 325. So now, when you look at the observed counts and the expected counts, you might see that a lot of the observed counts are close to the expected count, and maybe there are some discrepancies in some of them. Like for instance, I don't know, we're going to find out. The orange counts seem a little bit off. And I think maybe the brown counts are a little bit off. We'll find out if they're off to the point that we may be rejecting the null hypothesis. It's not enough to just look with your eyes. But remember, we talked about the alternative hypothesis. You could say at least two of the color distributions are wrong. So if one is wrong, there must be another one that's wrong. So in other words, there may be too many orange and not enough brown. It's the too many orange that was knocking the brown count down. So we'll find out. So the first thing you have to do is make a table of observed counts and expected counts. And all you do to get the expected counts is multiply the total times the claimed percentages for each color. Okay, the next thing that you do is calculate the chi-square statistic. So we have the Z score and the T score for the 1 prop Z and the 2 prop Z and the 1 sample T and the 2 sample T. So now we're adding on a chi-square into our list of statistics that they have us calculate. So how do we calculate chi-square? Well, it's quite the formula. Now the calculator is going to give us chi-square when we run the chi-square test. But as I've been telling you all along, when you're carrying out a significance test and a free response question, you have to play the game. You have to know the formula and show them that you know the formula. So we're going to do this one a little bit by hand to a certain extent. Chi-square is equal to the sum of O minus E, O for observed, E for expected, squared, divided by E for expected. So here's what that means. Take the first pair of observed minus expecteds. 138 minus 162.5 squared over 162.5. That's O minus E squared divided by E. Plus, take the next O minus E divided by E plus the next one. Oh, well, that's the same. 170 minus 162.5 squared divided by 162.5. And you just keep going until you finally do this last one. So 310 minus 325 squared divided by 325. You can even use this dot, dot, dot tactic. Show them the first two or three, show them the first one or two, and then do plus dot, 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 the last one. And they go, oh, she knows her formula. Now we're going to let the calculator tell us what that is, because I don't feel like doing that by hand. Okay, the next thing you need to do is make sure you state the degrees of freedom. Well, notice that the degrees of freedom is something minus 1 as well, but it's not sample size minus 1 like it is for the degrees of freedom on a t-test. It's number of categories minus 1. Well, if we come up here, there were 6 colors. So the degrees of freedom is equal to 6 minus 1 equals 5. Now, we're going to get the p-value from the calculator, and we're going to draw a picture of a chi-square distribution. Well, chi-square distributions are always skewed to the right. So we're going to have this in our work in just a few seconds from the calculator. So whenever you're doing a chi-squared test for goodness of fit, just draw x and a y-axis, and then just draw a little curve that's skewed to the right like that, and that'll be perfectly fine. And what you're going to do is, once you find out chi-squared, you're going to mark it and then you're going to shade to the right every single time. And the calculator is going to tell us what the p-value is, okay? All right, so how do we carry out a chi-square test for goodness of fit on the calculator? Well, the first thing you're going to need to do is press pause and enter the observed counts into a list and the expected counts into a list, and then press play, and we'll continue to run the test. All right, so now that you've got your observed and expected lists in your calculator, go back out to your calculator page, and just like any other significance test, press the menu button, go down to statistics, then go down to stat tests, and if you scroll down a little bit, you should see chi-squared GOF. You'll see two chi-squares. Choose chi-squared GOF. Okay. Now, this is lovely. All the calculator wants to know is three things. Where's your observed list? So tell it where, the name of your observed list. And then it says, what's your expected list? Tell it. And then it says, what's the degrees of freedom? Well, we know it's 5. And then all you got to do is click OK. And just like that, it tells you that chi-square is approximately 8.03. Just write it down. And now I can come over here to my picture and I can label this point 8.03. And now we're looking for the p-value. Well, the calculator tells me that the p-value is 0.15. A good bit of the region has been shaded. Well, that's just not difficult, is it? So now, isn't it time to draw a conclusion? We'll do that in just a second, but I think you know what I'm going to be saying. Now, the plan phase, where you check the conditions for a chi-square goodness of fit test, is very, very simple. 2 conditions. Were the data attained from random sampling? Well, if not, then invoke the 10% rule. So for ours, I'm not sure if these M&Ms are randomly placed into that big container that I used and placed them into cups, but I can say that 1,300 M&Ms is less than or equal to 10% of all M&Ms. Okay, so even though they may not have been a random sample, we can invoke the 10% rule instead. Are all of the expected counts at least 5? Well, I think so. Now notice it says all of the expected counts must be at least 5, so they are. Not the observed counts, but the expected counts. Okay, so those conditions have been met. We're now ready to draw a conclusion. Well, you know how to do this. Since the p-value, which was 0.15-ish, is greater than the significance level assuming 0.05, I don't reject the null hypothesis. Okay, so if I don't reject the null hypothesis, that means I like the null hypothesis and that there's no evidence of the alternative. The alternative is saying the distribution of the colors is not the same as the claimed distributions. So we can come down here and say that there is no evidence that the color distribution is not the same as claimed. You know how to write those conclusions. So the chi-square goodness of fit test is very, very straightforward. It's used when you usually see a table of observed counts, or all you've been given is a bunch of observed counts. If you find yourself having the urge to carry out more than one proportion z test, that's usually an indication that a chi-square test for goodness of fit could be used. So I'm going to end the video here, and in the next video work out 2 sample problems.